Okay, prove with math induction. Okay, here's a statement that says that if I add up the numbers, this is an arithmetic sequence, A1 is 1, and it looks like the common difference is 4. If I add up the first n terms in this arithmetic sequence, which means this term is the an, then the sum should equal n times 2n minus 1. Okay, the procedure for math induction is to verify first that this formula works for n equals 1. So, and I would definitely recommend you have these steps written down on your paper. First step, n equals 1. But you want to show that this formula would work if I just added up one term. And so you're either comparing this first term with what you'll get when you substitute n equals 1, or just plug in n equals 1 here, here, and here, and see whether this is the same. So 4 times 1 minus 3 equals 1 times 2 times 1 minus 1. That's 4 minus 3 equals 1 times 2 minus 1. So that's 1 equals 1 times 1. So that checks. Okay, 2. Once we know what works for n equals 1, we have to check to see if we assume it works for n equals some integer k, that necessarily means it works for k plus 1, i.e. the next integer. So we're going to need, in order to do this, to substitute. In our an formula, substitute k plus 1. And that is 4 times k plus 1 minus 3, which is 4k plus 4 minus 3, which is 4k plus 1. And we will also need sk plus 1. So using this formula for Sn, everywhere you see an n, put a k plus 1. K plus 1 times 2 times k plus 1 minus 1. Simplify. K plus 1 times 2k plus 2 minus 1, 2k plus 1. 4. Okay, it is definitely true in every case that if I take the sum of the first k terms in a sequence and I add the next term, that I should get the sum of the first k plus 1 terms. So what I'm going to do now is let's substitute for all three of these. Right? Sk is what I get if I substitute k into that formula. K times 2k minus 1 plus ak plus 1 we just calculated. That's 4k plus 1. And sk plus 1 we just calculated. That is k plus 1 times 2k plus 1. Okay, we don't know that this is true. At this step in the math induction, we have assumed that the formula works for when n equals k. And by using the formula there, that's the assumption. We assume it works there. We're trying to show that that means it works for sk plus 1. So there's a question mark. Right now we have to make the left-hand side equal the right-hand side. And then we'll be sure that the formula works for k plus 1. So we will have assumed it worked for k, we will have shown it worked for k plus 1, and that's the last part of math induction. So let's see. You can either try to simplify the right-hand side or the left-hand side to do this. Let's simplify the left first. 2k squared minus k plus 4k plus 1. 2k squared plus 3k plus 1. Okay, so we need to show that this is the same as this. And you could either factor what's on the left to make it look like that, or you could FOIL what's on the right to make it look like that. Most of the time, it's probably easier to FOIL. K times 2k is 2k squared. K times 1 plus k. 2k times 1 plus 2k. And 1 times 1 is plus 1. So 2k squared plus 3k plus 1. And those are the same. So again, we assumed that it works for n equals k by using that formula. We showed that it worked for s equals k plus 1 by making the left-hand side match the right-hand side. So in all, right, we verified it worked for n equals 1. We showed that if it works for one number, it must work for the next number. Therefore, if it works for 1, it works for 2. If it works for 2, it works for 3, and so on and so on. So this is true for all n. And that is the point of math induction.